I left the group of Professor Mattei then, who moved to northern Germany, and at that time I wasn't very confident. So I moved to Cologne, where I started my PhD with Professor Griesbeck. And there I stayed in the photochemistry area, which was important for me, and I investigated now a class of molecules known as the phthalimides. And in particular, I investigated photodecarboxylations, so reactions that involve the loss of carbon dioxide and the generation then of radicals, and these radicals can then do very strange things. And the whole concept is very nicely demonstrated by this amino acid. This is glutamic acid, and it's nitrogen protected as a phthalimide. Phthalimide is a not so common protecting group for amino acid, but for us it's also the chromophore. This is where the light goes. And when you do this reaction with acetone and the presence of a little bit of D2O, and that was known before I started in Cologne, you get these monodeutyrated, alpha monodeutyrated compounds out of it. Yield is very high. You can remove the phthalimide and you have alpha monodeutyrated amino acids. However, they are all racemic. So when you start with a chiral L-glutamic acid, you get a racemic product out of this. We believe that hydrogen bonding is involved here, and we were actually able to use cyclic voltammetry, so an electrochemical method, to show that may actually be true. So there is a hydrogen bonding here with the alpha carboxylic acid function, whereas the remote one there is pretty much swimming around further away. It doesn't know anything about the phthalimide. The whole chemistry changes if you're using not the bis acid, you're using the bis potassium salt. You can use the bis sodium salt as well, or the lithium salt, or the calcium salt, but the potassium salt somehow became the recipe, the in-house recipe. So now your product is not this or something similar. Your product is now this ring. And when you analyze it, you have now lost both of the carboxylic acids. First, the one here. So you're forming this without the deuterium because we don't offer any. And then this guy here further converts to this ring. And by doing so, it loses a second molecule of carbon dioxide. We were puzzling for a while why this is happening. You can make very long, very large rings when you increase the distance between the two. So we believe that as a working hypothesis that the potassium is like a bridging atom. It brings the head and the tail of the molecule together. Now, of course, this is very difficult in water and acetone. But it's only a hypothesis, and we were able to actually grow a crystal of such a chelate or template where the potassium indeed bridges the carbonyl group of the phthalimide and the carboxylic acid. So maybe this idea, at least for a very short time, that there is a U-shaped geometry happening with the help of potassium is not so bad. If you look at the mechanism here, although I'm not entirely correct, we start at the ground state. We then excite the phthalimide into a singlet state. And phthalimides, they undergo very efficient intersystem crossing, and we get triplets. Triplets is just another representation, but they have a longer lifetime. So you have a bit more time to do your chemistry. This happens if you irradiate a compound like, for example, N-methylphthalimide in acetonitrile. We don't do that. We do it in acetone, and the mechanism is slightly different. The result is the same. Ultimately, what then happens is, after this intersystem crossing, we have an excited part of the molecule, an excited phthalimide, and suddenly it becomes like an oxidant. It is able now to induce a redox reaction. From the carboxylate further here, an electron is jumping to the phthalimide, and you are generating a radical anion and a carboxy radical. And they are known to very quickly release carbon dioxide, and if they do that, you get a carbon-centered radical, and after intersystem crossing back to the singlet state, you can finally form a bond. You need then protonation of your alcoholate here, and voila, you get your final product. All right? And the quantum yield, so efficiency of this reaction is very high. 40 to 60% of these excited states are used to make this reaction. And only the rest well, loses the energy in other ways. And that's a quite high number. This electron transfer here, you can calculate if that is actually happening or not thermodynamically. There's an equation, like the Nernst equation. There is a Riemann-Bella equation. You can put in very simple data that you can take out of the literature for reference compounds. And if you do that for the oxidation potential of acetate, this delta G for the electron transfer is negative. And that means that this electron transfer step is thermodynamically feasible. So it makes sense to postulate it. We then went on, and for the cyclization, we discovered a huge variety of very interesting compounds. So you can make carbocycles. I think the maximum length we had was 13. So we can, with ease, make rings that are 13 atoms wide. You can make lactones. You can also introduce some heteroatom into the chromophore. You can make cyclic alkynes. This is what I did in South Korea with the late Professor Shim. Of course, here it depends on the ring size that you generate. You can put in a sulfur atom. You can get a very interesting range of compounds known as benzodiazepines, and you can also make cyclopeptides. And we have made cyclic peptides with a ring size of 26 and yields of 70–80%. And there doesn't seem to be any limit in making this cyclization. We also removed the Fenner ring, which is more difficult because you get competing 2+2 cycloadditions now. So what I want to show you is this is a very useful reaction. You can get a range of different products out of it. And then, and that was the main part of my PhD that has been very productive. I think I got a total of 20+ papers out of it. So Gambate Kudasai beat that. So I disconnected the chromophore from the carboxylic acid, and I created an addition reaction. And this addition reaction was as productive. So again, we tested whatever I could find in the laboratory as a carboxylic acid, and I was able to synthesize all these different molecules. Some were surprising, others were quite ordinary. So you could do an alkylation here, you could do an alkylation even in the presence of other groups. That when you want to do that with a Grignard reaction, for example, you have an issue with. The Grignard also wants to react with, for example, here the ester group. And we also discovered some very strange and unusual ring extensions that I just want to go into detail a little bit here and a little bit up there. So this was the reaction that I wanted to do. I was still a young PhD student. I didn't think very much. I just had a look in the lab, and I found these alpha-keto carboxylates. They're commercially available as sodium salts. So I thought if I put that into my photochemical reaction, I always get these acylated compounds. And acylation is something that I knew from my master thesis. However, when I did the reaction, depending on the R group, I got also this strange thing, and I got this alkylated product. So obviously, I have lost, in order to get here, not only carbon dioxide, I also lost a molecule of carbon monoxide. And these are the yields for a range of compounds. This is hydrogen, so the benzyl, isopropyl, secondary butyl, tetrabutyl, isobutyl, and methyl. And alkylation occurred for all of these guys here. So loss of carbon dioxide and carbon monoxide. For isobutyl, I got this strange ring extension product, and I got the acylated one. And in case of methyl, I only isolated this strange molecule. It took a while to really solve the structure. The NMR was very simple. And I only finally knew what the structure was when we solved the X-ray structure for one of these compounds. And then suddenly the NMR made sense. But still to this day, we don't really know how this is really formed. It involves two molecules of carboxylic acids. That's all we know. However, we can explain very nicely now with the help of radical stability why we sometimes get decarbonylation and why we sometimes have the other pathways formed. Of course, it depends on the R group now if decarbonylation is favored or not. It's in particular favored if you form a very stable radical here. So if you form things like the benzyl radical, or the isopropyl radical, or the tertiary butyl radical, then you go down the right route, you form a carbon radical, and you get then alkylation rather than acylation. Only when your acyl radical is fairly stable, the carbon-carbon bond formation can compete. And somehow from this initial product here, through a ring opening, this is what we believe, you create a second photochemically active compound that then somehow magically forms this strange thing. All right? The other thing is that was mechanistically interesting was the introduction of heteroatoms here. It's the alpha position of the carboxylate. So there's one carbon between the X and between the carboxylate. And we tested oxygen, sulfur, amides, secondary and tertiary ones, and also amines. And with the one exception, and that was the amine here, we got quite nice yields. 90%, 71, 73, 57. So oxygen was a bit lower, but it was quite nice. Only for these amino compound we got reduction. So there was photoreduction happening, but that was known anyway. Amines are troublemakers. It is mechanistically interesting because you have a competition here in this crucial electron transfer step. So you have either an electron transfer from the carboxylate, giving you the carboxy radical that undergoes decarboxylation, or you have electron transfer from X, and you form this radical cation, and then the carboxylate in alpha position becomes a leaving group, and you kick out carbon dioxide. You get the same radical, so what? Basically, it makes a difference if you put a second carbon between X and the carboxylate, but I'm not showing you that here. What you can do is you can use now the redox properties for X versus carboxylate to really calculate which one is it, the upper or the lower case. And we were able to determine, with the help of some analogs, of course, and a bit more thinking, a bit more chemistry, that the reactivity order was the amines reacted the most readily. The electron transfer step was very hexagonic, but they didn't give any clean chemistry. Whereas thioethers, they also then go the route via X, whereas from anything else, you have electron transfer occurring from the carboxylate, and you get decarboxylation from the carboxy radical. And that is important, for example, for the amides, because amides are everywhere in peptides, for example. And of course, we made cyclic peptides, and the amides never interfered with the electron transfer step. There we have some serious discussions with a group in Korea, and I'm looking forward to meet Professor Yoon actually at the Japanese National Conference later this year. And then, of course, we made a few bioactive compounds, just to get the interest of industry, and we picked a range of compounds known as the alkyl or aryl methylene isoindolenones. This is what they look like, and they are known to be very bioactive, either as a cardiovascular drug, as an anti-cancer compound, or as an analgesic. And we synthesized them on typical 1 to 5 millimole scales, 2 to 10 hours, in 2 to 3 steps involving this decarboxylation. So very simple. You can buy most of the starting materials off the shelf. And that is something very nice, it's particular for lazy students. You know, they don't want to synthesize the starting materials in 20 steps. They just want to buy it off the shelf, put it together, give it a good stir, and there's my product.